Okay, hello. Hello, good afternoon, 61C. Can you hear me? Can you hear me? Okay, good afternoon. All right. Unfortunately, Vladimir has to deal with, he was due to give the lecture on family emergency, so I'll be taking over for the next few lectures. Example of redundancy in action. So I'm going to continue talking about, today we're going to talk about MIPS, assembly code. So just a brief review of what we covered last time. So this is all part of these different levels of representation inside a machine. And we're focusing here at this level at assembly language. And remember, assembly language is the human-readable version of machine code, the next level down. When machine code is just strings of ones and zeros that live in the computer memory and they represent the program you're trying to run. So machine code is the lowest level of software. It's the software that the hardware actually executes, and you'll build a machine later that does that. Assembly code is a slightly easier to read form of that same machine code, so you don't have to type in lots of ones and zeros. The kinds of instructions you're allowed to use, any given processor has a set of instructions it understands, and that's called its instruction set. And in this class, the main one we're using for lectures is called MIPS. And this is an old instruction set that was developed out of work at Stanford, actually. And it's a class, it's one of these RISC-style instruction sets, where RISC instruction sets are simple instruction sets, and has a very rigid format, where every operation has one or two operands and writes to one destination. And almost every operation only works on registers, those 32 in the case of MIPS, special fast locations inside the processor. The only instructions that talk to the memory are separate load and store instructions that read values from memory, put them into a register, or vice versa. And then there's also branches, which we briefly touched on last time. We'll go back over them this time. So these are very primitive little operations, and these are the things the machine actually understands. When we write code in a high-level language, it's the job of the compiler to translate whatever complex code we write down into a stream of these tiny primitive instructions. Okay. So just to give you I wanted to give you a big picture, a reminder of where we are in the system. So here's the components of a computer, the hardware. We have the memory, your input and output devices here. We have the processor that actually is the brains that does the work. But here's the memory, which is just a bunch of bytes, a whole bunch of bits. And in these systems, every 8 bits is a byte, and that has a unique address. So the program and the data the program operates on are stored in that memory. While you're running this program, what's happening is the program is stored in memory. Let's go look at that. So it's just a bunch of bytes, the machine code program. So in MIPS, every instruction is 32 bits. It's 4 bytes long. That makes it simple for the hardware to fetch those from the memory system, right? So the instructions are just all 4 bytes long, 32 bits. They just stored there in that memory. And by default, the machine just kind of steps through sequentially. Every 4 bytes, it fetches an instruction and does something, right? Unless you do a branch. Another thing I want to give you a big picture about is when you write assembly code, that's the textual form of those machine code. And there's a program called the assembler, which takes that assembly code and converts it into the binary format the machine understands. And this diagram is basically the same as the diagram I gave you for a C compiler, except now instead of having C source code here, you have assembler source code. And the convention is that assembler source code has a .s as the file extension instead of a .c that you have for a piece of C source code. And so the assembler will take these, turn them into machine code files, and then you can link them together with object files and build a whole program. So you could write a whole program at the assembly level if you wanted to, and people used to do this. Increasingly, almost always these days, you'll use some form of higher level language, C or something higher level, to produce this program. But you can write everything just in assembly code and link with pre-built object files if you want. Okay. So when the processor is executing a program, what the hardware is actually doing is, one at a time, it's fetching the instruction from the memory. And how does it know where the instruction is? Well, there's one register called the PC, or program counter. It's a really bad name for this. It should be called the instruction pointer. Some machines actually do call it the instruction pointer, but a lot of machines, including MIPS, call it the program counter. That's just the register that has an address in it, an address of where you are in the program in main memory. So the PC points at some location in memory, and that's the next instruction that will get executed. Right? And all that happens in the hardware side is the hardware goes to that address, reads out the 32 bits that are there, and then interprets them as an instruction, and then does that operation, and then moves the program counter to the next instruction, adding 4 bytes to it, and so on. So that's basically the fetch execute loop inside the actual machine. This is how the hardware actually executes software. Right? So the trick is, all the software stack we build on top of this, all the higher level languages, have to ultimately translate their code down into this machine code that's stored in the memory that the hardware can execute like this. Right? So that's what's going on above here. All right. So that's kind of just to set the scene again where we are. Let's now go back to going through assembly code and machine code for MIPS and what the instructions are there. So the big difference between calculators and computers is that computers can make decisions. They can make branches based on the data they see. And so based on some value, you need to do something different. When you write programming language code, in the high level, it's written as if statements. If x equals 0, do this, otherwise do this other thing. Okay. In the assembly language level, the instructions, the primitive instructions the machine has to do that are called branches. And so this represents, you're taking a branch in the logic of the program, you're going down one path or the other. And in MIPS, there are basically 2 forms of a branch instruction. One that says, take a branch if 2 registers have the same value. So branch if equal. So branch if register 1 equals, if the value in register 1 equals the value in register 2, then go to this place. We'll talk a bit about how you go to some other place. The other place is given a label. That label is just text in the assembly file. What will happen is the assembler will figure out, when it's done building the binary code, which address that label corresponds to. And then in the branch instruction itself, the branch instruction has an offset that says how many bytes plus or minus from this PC is the target if the branch is taken, right? So inside the branch, so this is the assembly level view of the world. The assembly level view is I branch to a label. We'll talk later about the encoding, but in the actual machine encoding, the way the label shows up is as an offset that says how many bytes plus or minus from this instruction is that label, right? And there's a limited range you can branch to, right? So now, the way the branches work, if the condition is true, you take the branch and jump to the label. But if the condition is false, the branch instruction acts like nothing. You just ignore it and step to the next instruction, right? So only if the condition is true does it do something, which is go to the target label. But if the branch is false, you just fall through to the next sequential instruction address. Okay, that's how the branches work. So BEQ is the mnemonic they use for this instruction, branch if equal. There's also a branch if not equal. So you can branch if the 2 values are different. Okay, so those are complementary instructions. So that's one kind of branch, and that's what we call a conditional branch. So branch is something that you change where you go in the program based on some condition you check. Just said there's 2 of those, branch if equal, branch if not equal. There's also unconditional branches. And these are where you always go to the other location. So always jump to a label, right? And in the MIPS, the mnemonic for that is just a J for jump, right? So just always go to this other place. You'll see how then when you're writing code, you'll need this to just jump over stuff in the program. So let's start looking at how you translate a high-level language if statement, like in C, how you convert that into MIPS assembly instructions. So first of all, we'll make some assertions about the high-level variables, which registers they're stored in. Remember that at the machine code level and the instruction set level, the processor only knows about a very few variables, and those are called the registers. And there's only 32 of those in MIPS. In fact, there's only 31. Why is there only 31 actually? Because of the 0 register, right? So one of those registers, one of the 32 registers is register 0, which always has the value 0. And it also ignores, if you try and write to it, it just ignores it and stays as a 0. That's one reason they have it there. But what we're showing here is in this piece of code, I have 5 high-level language variables, F, G, H, I, J, and those are just allocated to these registers, S0, S1, S2, S3, S4. Just to remind you again, so these names, $S0, those are just convenient mnemonics that actually map to some actual register number. I forget what $S0 is. I don't know if it's 15 or 16 or something. So it's register 16 is $S0. And by convention, some registers we use for variables you want to keep around, some registers we use for temporaries, and to make it easy to remember that, we just use these symbolic names, $S0. But under the hood, that gets converted to some actual register number. Anyway, so these 5 program variables, we assume are being held in 5 of those registers inside the computer. So let's take a look at some C code. So we're doing a comparison. If I equals J in the C code, well, that would turn into a branch not equal, because if you think about the way you write the C code, let's just show up the whole thing. So just this little snippet, if I equals J, F gets G plus H. Now, just look at the C code for a minute. What happens if I doesn't equal J in the C code? Yeah, you just skip over that line, right? So in the C code, you wrote a condition. When this condition is true, then do this piece of code. But if the condition is false, you're going to skip over it. So the way you translate that into the assembly code is check for the opposite condition, branch if not equal to the exit, right? So this will then branch to the exit if this condition is false, which is the same as just jumping around this in the C code, right? But if the condition is true, then this branch condition will be false because it's the complement, right? If they are actually equal, that means they're not equal. So I'll just fall through, and I'll fall through and actually do the add. And then I'll add, F will get G plus H in the register, okay? Question? Right, good question. The question is, when it hits exit, does it just leave the program altogether or just the next line? So in assembly code, part of the textual syntax is you can specify a location in the program by some name followed by a colon. So this colon here indicates that this text here is a label. And in this program, there would normally be some other instructions here that would follow on. And so you'd just be jumping to that label, and you just keep going at the label to whatever instructions are written there in the assembly file, okay? Now, the labels are just symbolic, human-readable forms that you write in the assembly code. The assembler will then translate that to machine code, where that label will be turned into, it'll just be an offset of how many bytes do I have to jump from here to here in the program when it's stored in memory, right? But for the human, to make it easier to write the program, you can just use these symbolic labels, all right? Any questions? Okay. So yeah, the note here is that the condition you have in the high-level program, you may need to flip it when you're doing the machine code, as we did here, right? So I think the question is, could you use branch if equal and put a label on the add? You could, but you'd then have to, let's say you did that, you put a label here saying branch if equal to, do the add, colon. If the condition was false, you would fall through that branch. And so to do that, what you'd have to then have is another instruction here that skipped over the add. And what kind of instruction would you use then? A jump, right, an unconditional jump. So you can see here it's more efficient to just do it this way around, where you flip the condition and do a branch over the then piece of the code as it translates to machine code. So doing this kind of optimization is something that C compiler is very good at. It knows how to take high-level code and map it to the best sequence of machine code. And these days, there's very few programmers who can do better than the compiler at this. There are some. Compilers are not perfect. And humans can fixate on some small piece of code and figure out how to super optimize it. But in general, a compiler will figure out the right way around to do these branches for you. But in this class, you're trying to learn how the machine actually works. So you'll be programming down at this level in some of the assignments. Okay. Let's do a little bit more complicated example. So the same allocation of variables to registers. So now we have an if-then-else statement in the C code, right? So if I equals J, then F equals G plus H, else it equals G minus H, right? So there's two different things you want to do here. So notice how we translate this. If it's not equal, go to the else part. So now we have else as a label here. And in this else piece, we do the subtract. Okay? But if that branch condition fails, which means that these two are equal, you just fall through. And when you fall through, you do the add. F equals G plus H. But now you have to make sure, well, I want to make sure I don't do the else part. So I have to jump over the else part, which is why you have this jump if exit here. Okay, so now you can see why you need that unconditional jump in order to map, conditional code, high-level code into the machine code, right? Question?
Yeah, just kind of related to like what you're saying about like super efficient at translating the code. I was just wondering if they like learn, so every time could you have like some compiler that just had access to like all of these great compilations of code and maybe just like get better at compiling, or does it just do the same?
Yeah, so the question was, does a compiler learn from previous compilations what to do? Interesting question. So in some sense, they always do, because the people writing the compiler look at how well it does on the code, and they're the ones who, then rewrite the compiler. There are people interested in using more machine learning kind of techniques where you see how good it is. And actually, one technique you can use is, instead of using a compiler, you can actually generate many different variants of the code and time them and see how fast they run to do auto-tuning. And it's not usually considered part of the compiler, but you can do that to see how good code you can generate. The thing is, often when you're developing code, you worry about how long does it take to compile my code. Because every time I fix a bug, I got to recompile and then test the code. A lot of those techniques that give you ultimate high performance, they take too long to compile for a lot of code, so you want to focus on getting it right and making that compile, edit, debug loop as short in time as possible. It's only when you have really high performance code you worry about really tuning it like that. Question?
So what's going on in scripting language like Python where you don't see it?
So in a scripting language like Python, they're often what they call interpreted. And so what happens is, instead of taking the time to sit down and compile the code, you can instantly run the code. But what actually happens is you're kind of looking at the code as it goes by and repeatedly translating it to machine code, which is called interpreting it. So I'm looking at each block of code and turning it into machine code. What's nice, you can get going straight away. You only have to actually sort of compile the code you actually use. The problem is that you don't get that really high performance. Some things people do try and do is get better performance by if I've seen it once, I'll remember that, how I translated it, and maybe try and optimize that if I keep executing the same piece of code. So techniques there's sort of a spectrum between very dumb interpretation, always looking at all the characters, translating them every time I run that. So in the loop, I would do it every time around the loop, versus trying to look at bigger chunks and remember how I did the translation to make them go faster. I'm moving more towards being a compiler. But C is a language that's designed for everything's compiled ahead of time before you even start running it. And that does let you usually get better performance by doing that. But you do have to wait for the compiler to run to do that. Okay, question at the back? Okay, yeah, so get back to this question of how are the labels stored. So the labels are just in the text file, the assembly text file that you type in with your text editor. The assembler then sees where they are and converts them just into offsets in the branch instructions. The actual MIPS branch instruction has a field that says how many bytes plus or minus is the target of the branch if it's taken. And so the MIPS ISA, there's actually a 16-bit signed immediate inside the branch instruction, and that's how far you can jump in one branch. So we'll get to instruction formats in the next 1 or 2 lectures and how it's actually encoded. But you should separate out the label as something in the text file from how the assembler converts it to bits in the machine code, right? So here we're just showing the assembler text file, how you write it. Okay. So the two branch instructions that MIPS has, they only check for equality, like are they equal or not equal. And MIPS decided to do this because those are relatively simple checks. But in addition, sometimes you need to check magnitudes. Is this value greater than or less than another value, right? And so the way MIPS does this is they have a new instruction, new to us, called set on less than. And this is kind of like doing a subtraction. You take the two numbers, you see if one's bigger than the other by subtracting and seeing the sign of the result, right? Except instead of storing the sign, it just stores a Boolean value, 0 or 1, if one operand is less than the other operand. So here's the example syntax. So set if less than, if register 2 is less than register 3, the result is 1, else the result is 0. So you convert that comparison into a Boolean 0 or 1 value in the register. I say Boolean, but it's actually a full 32-bit word where the low bit is either a 0 or 1, and all the upper 31 bits are all 0, right? So set if less than returns a 0 or a 1 based on the relative magnitude of the two operands. So now you can take that instruction and combine it with a branch if equal to 0 to check if a value is actually greater than or less than each other. So say we had this bit of C code, if G less than H, go to something. This is using a go to in C, I guess. MIPS code, we will just have set if less than into a temporary register. So remember, the T registers are our temporary registers by convention. So T0 will get the value of 1 if G is less than H, held in these two registers. Then you do a branch if not equal to 0 to less. So that's equivalent to if T0 is not equal to 0, that means that G was less than H, and so then we should take this branch. Okay? So you can see here how something that looks like one statement in the high-level language turns into multiple instructions in the machine code, right? And it's one thing that architects argue about is what should be in the primitive instruction set. Should I have a branch on one less than the other? Or just a branch on one equal the other? Or just branches comparing one register against 0? These are things that architects argue about when they're designing instruction sets, right? Just happens to be in MIPS, this is the way it's done. This is the choices they made. So notice here that the 0 register, that's always 0, is being used here to build the comparison. So I'm comparing T0 against 0. So the branch instruction can only compare two registers. There's not an immediate form where you have branch if equal to an immediate. Right? Remember, immediates are these bit patterns that are encoded in the instruction directly, constants encoded in the instruction. For branches, you could only compare two registers. And so it's very convenient to have one register that's always wired to 0. So you can always compare a register to 0. So this was a set less than instruction. This takes two registers and treats those 32-bit binary numbers as signed integers, right? 2's complement signed integers. There's also a set less than unsigned instruction that treats those two registers as unsigned values. Remember, if you're comparing the magnitude, if you have a signed number, a negative number is less than a positive number, right? If the high bit is set, it's negative. So that number will be less than a number that has the high bit 0 because it's positive. But if you have unsigned numbers, if the high bit is set, what does that mean? What kind of unsigned number is it? Is it big, small? It's big, right? So if the high bit is set, that means in an unsigned integer, that means it's a very big number. So a number with a high bit set compared against a number with a high bit low, if they're unsigned, number with a high bit set is greater. So this is just to hammer home the point that in the registers, you just have bit patterns. It's the instructions that operate on the registers that interpret them in a given way. So a set less than instruction interprets them as signed and tells you whether one's bigger than the other. The set less than unsigned instruction interprets them as unsigned and tells you whether one's bigger than the other. The register values could be the same. You could do set less than on one pair of registers, set less than unsigned on the same pair of registers, and get two different results. Okay. So one thing you can do, I said there's no immediates in the branch instructions, but there is a form of set less than that has immediates in. So you can compare whether a value is greater or less than a constant in one instruction. So one example here is set if S0 is less than 1, the constant 1, then you'll get a 1 or a 0 in the result T0. Then you can check that in a branch. Okay. Okay, so that's just saying you can also have immediates in the set less than instructions. All right. So that this, you might be asking yourself, why do they do this? Why do they not do this other thing? And there's actually a lot of different design choices. Different instruction sets do this differently. That's one reason why you can't run the same binary code on one machine and the other machine, right? And architects will argue about this at great length. In the big picture, it doesn't really matter too much what's actually in the instruction set. But these differences are just somewhat arbitrary. Don't worry too much. Panic about not quite understanding why they did this versus the other. They just decided to do it for whatever reason. They had arguments and somebody won, and that's what went in the instruction set versus what wasn't in there. But they're all designed to be very small, primitive, easy to execute operations. Okay, let's do some clicker time. So I've told you about how to translate if then else's. Now, another kind of control flow you have in programs is loops. So this is a piece of assembly code that implements some kind of loop, C loop. And so your assignment, first is try and do this by yourself, is figure out which kind of loop this is amongst those choices. So while, do while, for, it's not a loop, or it's none of the above. So then we'll give you a few minutes to think about it, vote on it, then I'll give you another chance with peer instruction. Okay. Okay, 2 minutes. Be the end. Okay. So let's take a look at the results. Okay. B is popular, but there's a few other ones. Let's see if people go with B or change their minds. I'll give you another couple of minutes to chat amongst yourself. Try and convince your neighbor that you're right. Okay, people settling down? All right. Wow, very quiet. Okay, well. Okay, that is probably their answer. So let's go over this. So actually, it's very difficult to tell what it would be if you actually took a real C compiler and compiled the loop. But based on what's given here, B is the most plausible explanation of what the loop is. So look what's happening. Your the only branch is here, right? So if some condition is true, you're jumping back to the label. So this is doing something and iterating until S3 equals S2, right? So do while S3 is not equal to S2 is basically the form of this loop. So it does the loop at least once before it does the while to checks the condition. Yes. Sorry, I couldn't hear you. Say again. The line with the load word is loading a word. Does anybody know what this code is actually doing? That's incorrect. I know what the code is doing. Right. Right. It's actually summing the numbers in an array. So what's happening here is this is shifting this number by 2. So shift left logical by 2. That's multiplying S3 by 4. And that's because you're going from an index to a byte address into a vector. It's then adding this value to something called S5. S5 is the base of the array. It's like a pointer to the array. So you're adding the base held in S5. You're adding this offset that you've just calculated in bytes to it to get an address of a word in the array. Then you do a load from that address. So I take that address I just calculated. I do a load word from that address, back into the same register, back into T1, a temporary. That value I just loaded, I added into S1. So S1 plus the new value goes into S1. So I'm accumulating those values into S1. Then I'm just checking to see, I'm adding to S3 some value in S4. So there's some stride here. So S4 could be, 1 element, 2 elements, 5 elements, 37 elements. So you're striding through the array by adding this to this index. And then you're checking here. You must have set this up beforehand to know that it will finally hit some value S2 at which you can exit the loop, right? So this is a little loop that's striding through an array and summing some of the elements to give you the result. Now, why is it a do while? It's a do while because there's no condition until at least one time through the loop. So you hit this loop, you go straight through until the end when you do the first possible place you can exit the loop, right? A regular while loop, you first do the check before you do anything. But a do while, you do it once before you do the check and then come back. Yep, question?
What in this code, made you think that it was an array? You know what I mean? Because I looked at it, I was like, okay, that, it should be a integer, getting multiplied by 4 and stuff like that. What makes you say it was?
Well, you have to look at the whole pattern of the code to understand it. I've stared at much too much assembly code, probably. But if you just go through, one thing is true, it's very difficult from a little piece of assembly code to figure out what's going on because, you translate large chunks of, a small amount of C code may turn into a large amount of machine code. So it's difficult to look at a small piece and really understand what it's doing. So you have to understand the whole loop to really understand that each piece of it is doing whatever it's doing, right?
So why couldn't this be an integer?
Sorry, say again?
Why can't it be?
Why can't it be an
Integer, like that we're dealing with.
Well, these are integers. You see, this instruction add is an integer add instruction. So you know from that opcode that it's treating the values in the registers as signed integers. So it's adding signed integers to signed integers. That's what it's doing. That's what the opcode tells you, right? Any other questions about the code? Yes?
So, what's inside register S3 is the sum of the array?
S1.
S1. Okay, sorry.
Yes, so you see S1, you're adding S1 to T1, then storing it back into S1. So, it's like X equals X plus next value in the array. And you just, around the loop, you'll keep accumulating it back into S1. So the next time around, you get the new value of S1 and add that in, right, as you go around the array. Any questions about the code? As you start writing more assembly code, you realize there's only certain ways to write certain things, and you'll get better at pattern matching. This is what that assembly code must be doing because that's the only obvious, only thing that will happen. But like I said, you often have to look at quite a few assembly instructions because it takes quite a few to express something in the high-level language. Like each individually are pretty primitive. Just to sort of hammer on this a bit. So notice there's 3 add instructions in here. Okay. So think about, they're all basically doing the same thing, just adding 2 integers together. But what do they mean in the context of the high-level program? This first add is used to do indexing. So in the original program, there was probably something like, array, square brackets, index I. And this add here is basically adding the offset to that base address to give you that square bracket indexing into the array. This add is actually summing the integer values, sum equals sum plus new value. So it's doing what you would see as an arithmetic operation in the original high-level code. This last add is striding through the array. You're updating the index variable to the next element. So, from the high-level programmer's view, these are quite different things. I'm doing different kinds of things of different types. But the machine only has a few primitive operations that, you map it down to the same set of these few primitive operations. Right? So it's only by knowing the context you can see what these individual instructions do, right? But at the high-level language level, you can write arbitrarily complicated high-level programs. There's only like a few dozen instructions needed. And you can compile any high-level program down to a few dozen instructions, right? In fact, you can actually get by with a single instruction of a particular kind and compile any high-level program into it, right? But it's actually more efficient to have a few more than just one instruction, right? Okay, let's do a bit of administrivia. So hopefully you've all done with homework 0. Homework 1 is due on Sunday. Like we warned you on Tuesday, if you haven't started it now, you should start it right now. It's not an easy homework. It takes a bit of time, especially if you have never programmed in C before. Okay. Okay. Let's take a 2-minute break. You guys have earned it. Okay, let's get going again. All right. Oh, I should have done this first. Okay, so in the news, you now get a very cheap board with a MIPS processor on it. So this is like your little Arduino or a Raspberry Pi, but with a MIPS CPU on. And this supports Linux and Android. So if you want to actually have a real MIPS processor to use, you can go and buy one of these. I think they're pretty cheap. Anyway, when you get this MIPS board, one of the things you're going to want to do if you write an assembly program, or if you're compiling C code, is call a function. Right? So far, we've just given you very simple snippets of code that would be in the sort of middle of the body of some function somewhere. But when you're writing big programs, you break them up into functions, and a function has to be able to call another function. And these subroutines, you have to be able to return from a function back to where you were called from. So how is this arranged at the assembly code level? So this stuff, the rest of this lecture is a little bit involved. Hopefully we can get through, and you can see how the whole magic of procedure call return works at the machine level, and instruction set at the machine level. So one thing, bit of historical note. So the idea of a subroutine, it was actually this guy Wheeler, who was at Cambridge, UK, and he worked on EDSAC. Remember the very first stored program computer, the very first computer that stored program as numbers in memory? They started writing code and realized, I think we need subroutines. It's kind of, we can't just have straight line code. We're going to write substantial programs. And he actually invented the subroutine, right? This guy Wheeler invented the subroutine, and it was called the Wheeler jump, because you could jump to some piece of program and jump back again, then reuse that same piece of code at many locations in your original program. Because prior to that, what you would do, what would you do without a subroutine? You just copy the code everywhere, right? So every time you need a sign function, you just copy it in line every time you needed it. Or back in the old days, you would just get a set of cards with the numbers punched on them and punch a new set and just insert those into your card deck as you loaded the program. And remember, those early machines didn't have much memory, so that was pretty inefficient. Also, if you got a bug in one part of your program, in one version of the routine, you have to go fix all the other ones, right? So subroutines are a really great idea. So one little anecdote. So Wheeler, I actually went to talk to him. I was thinking about doing a PhD at one time. I was at Cambridge. I actually went to see him, and people warned me about going to see Mr. Wheeler. He's a little bit odd. He's been around for a long time. I went to see him, and he was a very nice guy, actually. I had a long discussion with him. But he said, computer architecture is dead. There's nothing to do. We invented it all already. Go do something else. So I didn't listen to him. I came to Berkeley instead. But I did actually meet the guy. He's a very nice guy. But he invented the subroutine, right? So it's amazing that, this field is so young. We know the people invented everything, right, in the field. Pretty amazing. Okay, so if you're calling a function, what do you actually have to do? You have to put the arguments somewhere the function can find them, right? So when I call a function, it has a list of arguments, and the code inside the function has to know where the arguments are. So you need some convention on how a function finds the arguments it was called with, right? You have to actually then jump to the function, right? So I have to pass control or somehow jump to the code where the subroutine is located. The subroutine itself has a bunch of local variables. So you have to allocate space for those local variables inside the function. Okay? So where do we allocate those? Local variables in the function, where do they live? The stack, right. So we're going to allocate that on the stack. Then once we've done all this, we've created the arguments somewhere, we've jumped to the code, we've allocated space for its local variables. Then we can actually run the code inside the function. Once we're done, we have to take the result that function produces and put it somewhere that will return it to the caller, right? Because you were called to do some function on behalf of some other piece of code. You need to get your value, return it back to that other piece of code somehow. And then you actually have to transfer control back to where you came from to end the subroutine call, right? So all these steps have to happen to call a function in your high-level program. So we're going to go through and see how this actually happens in the assembly level on the machine. And we'll need a few more instructions to make this work. One thing that happened in early computer architecture was the very first machines didn't really have good instructions to support subroutines, and they kind of had to invent that as they went along in the early days. So MIPS, so every type of processor usually comes with what they call a calling convention, which is for that particular processor and that instruction set and the compilers for that machine, they've sort of agreed on how functions should call each other. Because remember, these may come from different places, different people, right? So you have library code coming from wherever, and it all has to obey the same standards, so you can easily interoperate and call any piece of code from any other, right? So we have these, what we call these function call conventions. So in MIPS, it has this big set of registers, 32 registers. That's actually a lot compared to some early machines. So you want to use those where possible, because those are much faster than memory. And so at MIPS, what we do is we assign 4 of those registers to be what we call the argument registers. So we give those symbolic names, A0 through A3. So A0 through A3 are 4 registers we use to pass arguments to routine. We're going to dedicate another 2 registers to hold return values. So you can actually return 2 values at a time from a function, or an 8-byte value from a function in 2 registers. And we call those V0 and V1 for value, the value the function returned. We're going to dedicate another register to hold the return address. So remember, when you call a function, the function has to know where to go back to when it's done. And so the caller, the piece of code making the call, has to record its address in a register, the program address in a register. So when you call the code in the function, it knows where to go back to when it's done, right? So, and in MIPS convention, the register is given the symbolic name RA for return address. So one of the registers is allocated to holding this return address when you're in a function. Okay, so let's start working through this. So say we have a little sum routine. So all this function does is takes 2 arguments, adds them together, and returns the result. Okay? So notice it has a type int on the function, so it returns an integer, has 2 integer arguments, and those are passed by value, right? So you actually copy the value into those new places named x and y in the function. You return the sum, and then you just call this in your other code just by saying sum AB, right? So, as I sort of mentioned at the start of the lecture, in the machine code for MIPS is all stored as 32 bits per instruction, so they're all 4 bytes long. They're just stored in memory sequentially. And what we're showing here is just the decimal addresses of those locations. So, address 1000, 1004, 1008, 1012. That's kind of where in the memory the program is being stored. So this is we're just starting to build up on this function call. So I'm going to take it in steps. So what I'm showing here is this instruction here. So this is written as an add, but notice the add is adding some value to 0 and putting the result in A0. So if you add 0 to a value, what are you doing? What does the result equal? The original value, right? So all this is really a copy. I'm just copying the value that's in S0 into A0. So S0 is one of the variables in the program, and I'm copying it into the argument register, right? So I'm initializing the argument register that's going to be X in this case with the value of this variable A, okay? So that's where call by value is happening, right? I'm taking the value of that variable and transferring its value into the argument register, right, to initialize it. I then do the same thing for the second argument, so y equals b, just another add, a different set of registers. So I'm initializing A1 to have a copy of the value in register S1, which holds the variable b in the program, right? So notice I'm calling this sum AB. Inside this function, when I call the function down here, it's going to use A0 and A1 as where its arguments are, right? So now what I'm going to do is record the place to come back to. I have to remember my return address. And so here I do an add, where I'm adding this value, 1016, to 0 and storing it in RA. This is, so notice this is an add immediate. I mean, you can store immediates. You can add immediates. So adding immediate to 0 just copies that immediate into a register. Right, so now I've initialized RA with the address I want to return back to. Then I do a jump. And that jump takes you over to the function code, right? So somewhere else in the program, in the memory, is the sum subroutine, right? Over here it's at location 2000. So in the MIPS jump instruction, there's a field that gives the sort of bits that hold the address that you're jumping to. So you just jump to address 2000. And here is the code inside that, the code for that subroutine, right? The code is just one instruction to do the add. So add A1 and A0, place the result into V0. Remember, that's the return value from the function. So I'm done with the computing here, x plus y. Then this is a new instruction, jump register RA. So jump register is a kind of jump, but it doesn't jump to an absolute address in the program memory. It jumps to a location that's given in a register, right? So RA holds an address, it holds a pointer to the program, and what you're going to do is tell the machine, go start fetching instructions from the address whose value is given in register RA, which effectively takes you back to this location 1016, right? So this jump register RA, given that RA was initialized to 1016, when you hit this instruction, it'll jump back to here. So why didn't we just put 1016 in here, jump to 1016? Why do we initialize this RA register?
Because if you add more code before it, then all the previous lines shift.
Well, one thing might be, yes, sure, if I added more code in here, the number would shift. But what's the bigger reason why I don't use? Right, so the reason we do it here, rather than just have a return number here, is that you want to call this subroutine from many different places, right? So the whole point of having the subroutine is you can reuse it many times in your code. So each point in the code is going to be at a different location. Every caller is going to be a different memory location. So it should encode its own location, call the subroutine, then the subroutine jump back to where it was called from. A different location will code its location. And then you can return back to that different location, right? So the whole point of a subroutine is you can reuse it from many different call sites in your program. So you cannot put one single number here and make do with that. So getting back to the Wheeler jump, so the original EDSAC didn't have this jump register. And what you had to do was actually modify the program. So here you would actually write this number into this jump instruction. So you kind of modify the code of the subroutine you were calling and say, I'm going to poke this number in there, so I'll call you, then you'll come back to me. And the next guy who called it would have to go overwrite that same location. All right. Question?
Is there an actual difference between the RA register and other registers? Like, could you use a different register for it, or is it just convention?
It's just the convention. It's a good question. So, and in fact, for all of these names, dollar whatever, except for the 0 register, which is hardwired to 0, all the other registers, it's just a convention that we allocate them to one purpose or the other. You can use almost all of them for any purpose. Having said that, RA, there is one special thing about RA, and we'll get to that. There's an instruction that's designed to write to RA that one register in particular. It's called the jump and link instruction. We'll get to that next. Question at the back? Sorry, I heard when it goes back, it jumps back to 1016. I didn't get the rest of your question. So when you return back to here, the result will be in V0. A0 and A1 will still hold whatever they had before, right? But the code here by convention at 1016, that code knows to look for the result in V0, right? Question? So it's a good question. So where it says conventions, the fact it has 4 arguments and 2 return values, basically any code compiled by the C compiler or that's handwritten assembly code, you obey that convention so you know that the code can call it. You know that you can call some other code. That code knows how to call you. You could try to do something different. It would just break the calls, right? You might find in some occasions people might write custom calling conventions for some special little routine. That's pretty rare. Usually just use the standard one on the system, right? But these are all just conventions. The actual set of instructions is very small, and this is just software's way of using them to implement this high-level language feature, right? Okay, I think we've done some of this. So notice in the example I gave before, we use this way of encoding the return address by doing a separate add immediate, and encoding this absolute return address here, right? And then we jump to the thing. What the MIPS actually has is another instruction called jump and link. And that's designed to do both of those things at once. So in one instruction, you jump to a location, right, the label, jump and link to some, but this instruction at the same time writes the return address. And actually, this is one case, this is the case I was saying where R31 is different. The return address register is different because it's implicitly targeted by this instruction. So jump and link jumps to the subroutine address, but writes the $RA register, which is register 31. It writes that with the return address, right? And the reason it's implicit is they wanted to save bits in those 32 bits. They wanted to save some bits to make the jump offset be larger, right? So you could jump to a greater range of memory addresses. So they made that range bigger at the expense of having to hardwire in the return address goes to register 31, right? So something that software can't really change, this instruction overwrites register 31, which is given the symbolic name $RA, right? So $RA lives in register 31. So that's kind of hardwired into the ISA. So why do this? Why not just use these two instructions everywhere? Well, calling subroutines is actually pretty common. And this is, saves code size and actually is faster to execute. The one instruction does two things, right? So the architects made a decision to have this one single instruction do both those tasks. Okay. Okay, so now we have this jump and link instruction to call a subroutine. The slide says it's really link and jump because you build the link first before you go to the subroutine. Remember where you are before you go to the other place, right? We already said this, that all of this stuff. Oh, there is this other form. So jump and link goes to an absolute address or goes to a byte address you encode in the instruction. As with the jump register, there's also a jump and link register instruction. Oops, no, this is jump register. Okay, sorry. So jump and link stores the register in RA, the return address in RA. And we saw already this jump register instruction will jump to the address that's held in the register. So the program will go to the PC. We'll set the PC equal to the value in that register. Jump register, this doesn't have to be RA. You could jump register to any register. But the jump and link only writes to RA, right? You could copy RA to some other register and then do jump register to that other register, right? But jump and link only writes to RA. So this is kind of getting onto the convention. So the caller, the thing that's invoking the subroutine, puts the arguments into A0 through A3, then use jump and link X to go to the address of the subroutine in X. So I kind of already told you this, but there's a program counter which is keeping track of where am I right now. So the computer hardware, the processor needs to know where in memory am I currently executing instructions. And that's the value that's placed in the link register. Now if you think about it, which PC should I put in the return address? So if I'm the jump and link if I'm the jump and link instruction, and I'm at location decimal 1000, I'm going to call some subroutine. What value should I put in RA for the subroutine return to? So I'm at 1000. Sorry. 1004, right. Because you want to return to the next instruction. If you put 1000 in, you would come back, you would call it, you would come back, you would call it, you never get out of there, right? So you have to put the return address to be one past the jump and link instruction, right? So the jump and link writes the following instructions address into the return address. And then jump register on the subroutine side, you do jump register return address to come back to where you came from. Now, when you write a function, you don't know where it's being called from. You don't want to know where it's being called from, right? I write some nice new library function. I want to use all my local variables, do everything with it. I don't want to care about who calls me. And also, I don't want to care about, if I call some other function, what it does to my variables, right? So, locally within each function, you declare some set of variables that you operate on. And you want those to hang around because you're relying on them while the function's in execution, right? But when you call a different function, it's going to want to, allocate its own variable space, right? And, the fastest place to hold variables is in registers. So everybody wants to use the registers, but you only have 32 of them. Right? Finite number. Well, 31, excluding register 0. So all these different subroutines you're calling and returning from, they all have to share the same set of registers. So we need some kind of convention across all the functions on how they're going to share those registers, right? So the basic idea is when I call a function, if it's going to use some register, it has to save the value that was in there before and restore it before it returns. So kind of, it's okay to use the register, but you have to put it back just like you found it, right? When I return back to the other guy, it doesn't know what happened, right? So you need a place to save the old values of the registers before you stomp on them with your own new values inside the function, right? And then you restore from that place when you go back. And this is all held on the stack, right? So the general idea in the stack, when I call a function, I'm going to push onto the stack some values, and I can save all the old values that I'm going to overwrite. And then when I'm done with this function, I'm just going to read them from the stack, reload them, and then just push the stack back, and I'm done with the stack entry, right? Now, you need to know where the stack is. So in MIPS, there's a convention that one of the registers is designated SP, the stack pointer. So again, this is a software convention. In this case, you could choose any register. In MIPS, the convention is register 29 holds a stack pointer, and we give it the symbolic name $SP, the stack pointer, right? And this just points at where the stack is currently in memory. So the function knows where to find its local variables, because everything is done as an offset from the current stack pointer, right? And in MIPS, the convention is you go from high addresses to low addresses. I saw on Piazza somebody wanted to go the other way for some reason. I think MIPS goes this way, right? It grows downwards. Just fact of life, right? So when you're pushing new stuff onto the stack pointer goes down. And when you're popping stuff, it goes back up again, right? That's how you allocate and deallocate space on the stack. And it's all LIFO, right? Last in, first out. So just a little example. So this is what we call a leaf routine. A leaf routine is one that is a subroutine that can be called from other places, but that doesn't itself call any subroutines, right? It's kind of at the end of the call tree. Like you can call this function, but you know it doesn't call anything else, right? It just does some local computation and then returns. So it has 4 arguments, GHIJ, and those are held in the argument registers, A0, A1, A2, A3. We're going to use a local variable F. We're going to put that in S0. I'm going to say we'll use a temporary register T0. Okay, so locally, as well as the arguments, we're going to use a couple of local variables, S0 and T0, inside this function, okay, to do the calculation. So one idea is what we're going to do is, when the function is called, there's some stack pointer here. When I call a function, I allocate space, and all I have to do to allocate space is decrement the stack pointer, right? I make the stack pointer point a bit lower down in memory. Stack's growing down. Those locations I can now use to hold new values for this function. And I'm going to store the values of T0 and S0, do whatever I need to do. Then when I'm done, I'm going to return and push the stack pointer back up. Right? I'm done with that bit of memory. Now a different function can be called from that caller, and it will reuse this space, but to hold something different in here. Right? So I've allocated it for the duration of the call. When I'm done with it, I can return and deallocate it. Right? So somebody else can use that space. So let's look at the MIPS code for that leaf example. So the first thing we do is allocate space on the stack by decrementing the stack pointer. Right, so stack pointer is just a convention that this register holds a stack pointer. So I'm just going to decrement it by 8. Why am I decrementing by 8? Right, I'm holding 2 words. I'm saving 2 registers, and each register is 4 bytes. So I need 8 bytes of space on the stack to hold those, to store those 2 values I'm saving, right? So I decrement the stack pointer by 8. I then store one of these guys with an offset of 4 from the stack pointer, the other guy with an offset of 0 from the stack pointer. So I'm just copying out the old values to memory so I can reuse the register locally inside this function to do some work, right? So I'm just saving the old values to memory. I then do the computation in here, just a bunch of adds and subtract. And notice I'm reading the values from the argument registers, and then I'm writing the result into the return value, V0. So I'm done with the computation now. And now I just have to patch things up to return. So I patch things up by reading the old values from memory, from these locations on the stack. I then put the stack pointer back, just add 8 to it. I subtracted 8 at the beginning, I add 8 at the end. So the stack pointer ends up back where it came from, right? And then I do a jump register, return address to go back to the calling routine, right? So now I've managed to create a little local stack frame, save stuff, do my computation, calculate the return value, restore the stuff I saved, and jump back to where I came from, right? So now the calling routine can carry on. It doesn't know that T0 and S0 were saved and restored. It doesn't care. The values are there. They're left in there. So it doesn't know that you played with them in the meantime, right? So that's the convention. You have to look after the things you messed up. Okay, what if you have... So that was a leaf routine. So a leaf routine is easy because although it gets called from somewhere, it doesn't call another function. What if I get called from someplace and in turn I call another function? This is very common. You write a lot of code that has function calls in every function, right? One thing to think about is, well, the argument registers, I'm reading the arguments coming into my function, but if I'm calling another function, I need to set up its arguments, right? And those are the same registers, A0, A3. Those are being used both for my arguments coming in and to send arguments to functions I'm calling on the way out, right? So again, the idea is you just have to save this stuff to memory if you don't want it to get stomped on, right? So let's take a look at a little example of 2 nested procedures. So here's one function, sum square. And what this does is adds the square of x to y. And the way it does this is by calling another function, multiply, that multiplies x by x. Then we add y to it in here, right? So this one function, sum square, is calling another function, multiply, but itself is a function, right? First thing to think about is, well, when I call sum square, I tell it return address I want it to come back to, but then it has to call multiply and tell multiply to come back to sum square, not to go back to the original location, right? So I have to remember where I was called from, store that away, so that I can then call multiply and have it come back to me, right? Okay, so the general idea is you're going to save all this stuff on the stack. Just to remind you, there are different places data is stored in a C program. There is static stuff, which are variables that live for the whole duration of the program, and they're just allocated out in memory someplace, just statically allocated when the program is compiled. This is where they're going to live in memory. There's the heap where you do malloc and free to allocate and deallocate space dynamically, and those objects live for as long as between the malloc and the free, so they can live across function calls. And then there's the stack, which is used to hold all the variables that are local to a function and only visible inside a function. So they disappear once the function returns. Okay, and that's where we're also going to save all this internal machinery. There's the variables the programmer wrote about. There's all this internal save and restore that's happening just to make the machinery of function call work, right? You don't really see that as a programmer, but it has to be there to make things work. So you call functions a lot when you write programs. Your well-written program is broken down into, reasonably understandable functions. And so real programs in real life, you spend a lot of time calling functions and returning from them. And so compiler writers will spend a lot of time thinking about how to optimize this process because it happens so often when you're running a program. And so MIPS has the calling convention we gave so far is not quite accurate. There's a bunch of optimizations they've done. And what they've done is said, well, we're going to divide the world into registers that you have to preserve across a function call versus registers you're allowed to stomp on. Because what they observed was, well, I'm not using every register, so it's okay for callee, the thing I call, to stomp on some of those. I wasn't actually going to use them anyway. But you need to balance that with, actually, there are some registers I need to hang around. So you split the world into registers that are preserved across a function call and registers that are not preserved. So the way this happens in MIPS is that RA, SP, GP, FP, we'll get to these later, save registers S0 through S7. So all these registers, a function has to save and restore if it uses them, right? If you don't use them, it's fine, just leave them be, and they'll have the original value when you return from the function. The real constraint is they have to have the original value when you return from a function call, right? So those registers are in that category. The other category, though, are registers that the calling program cannot rely on. So the function you call is allowed to modify them without putting back the original value. right? So the caller cannot rely on them. And those are the return value registers, V0, V1. That makes sense, right? Because I'm calling the function to return a value in those registers. I can't rely on some value I had in there staying around. It's going to be stomped on by the function returning the value, right? So those are in this category. Also, the argument registers, so A0 to A3, the function can overwrite those without saving and restoring them. And finally, there's the temporary registers, T0 through T9. These are also sort of just, free space anybody can stomp on any point in time. So you cannot rely on them surviving across a function call. And all this is just a convention. So the compiler writers have figured out this is a reasonably good trade-off by splitting the registers between ones you have to preserve, ones you don't preserve. You can kind of sort of get pretty optimal calling sequences. Okay, back to clicker time. So which statement is false? I'll just run this thing, see how you do. Okay. Let's see how people did. Okay. So I think this is a case where it'd be really good to talk to your neighbors and see if you can clear up. Like, a lot of choices are popular here. So just to remind you that the caller is the one making the call. The callee is the routine being called, right? Caller, callee. Let's run this for another 2 minutes. Okay. All right. So, okay, so pretty clear winner here, though there's still a few people wondering about this. Let's go talk about this a little. So this is true. You use jump and link to invoke a function, and jump register to return from a function. That's true. That's how you get there. That's how you get back. This is false. So you save PC plus 4 because program counter is in bytes, and each instruction is 4 bytes long. So you need to move it by plus 4 to get to the next instruction. The reason they're called temporary registers is because the callee can just use them without saving and restoring them. The caller cannot rely on them. They're just going to be stomped on by the routine. That's okay. And you can rely on these save registers. The S actually means save registers because the callee has to save and restore them if it messes with them. Okay. Okay, so we talked a little about allocating space on the stack. What we call automatic variables are all those variables that are local to a function allocated on the stack. Like you automatically get a new copy when you call a function, whereas the static ones exist across wherever. This is just terminology. So that thing you create, when you move the stack pointer down, you create this whole chunk of space into which you write things. There's actually convention for how things are laid out within that block, and that's called the stack frame, right? Just the layout of that block of data you allocate on the stack is called the stack frame, or sometimes called the activation record. And in some cases, you can just with a single immediate add, because you know ahead of time for this function how much space it needs. So you can just add immediate to the stack pointer to give you a constant size increment. Sometimes, if you don't know how big things are going to be in the stack frame, you have to allocate what's called a frame pointer to keep track of how big the stack got. And that's a separate register. You don't always need that. Let's just give you a picture of what's going on. So you have the stack pointer here. When I decrement the stack pointer, I allocate. There's this convention of where things are put. You don't just put them anywhere. You put them in defined places. And the reason is that when your program crashes, you can do what's called a stack trace and go back and find out, how did it get here? Why am I in this routine with these values? Well, I can go look at the stack and see what was the path of calling this routine and what were all the arguments on the way down. And the debugger relies on the compiler having put things in known places, so we can kind of trace back and figure out what happened. So local arrays, saved registers, saved return address, saved argument registers. They're all in this standard location on the stack, so you can go uncover them later. Okay, so we'll do this next time, all right? See you next week, Tuesday.